the chain rule and derivatives of exponential functions. The goals here: understand the chain rule for derivatives, and then know how to find the derivative of an exponential function. And you'll see these two go hand in hand. The way that we're going to develop the derivative of an exponential function will require the chain rule. So that's why they're put together here. And the chain rule itself, what is it? Well, the chain rule is used to find derivatives of composite functions. So recall that a composite function is defined as this f of g of x equals f with the g of x plugged into it. And you can think of the inner function here, this g of x, as w equals g of x. And then the outer function would be the f of that w result. So you'll see I'm going to use this w again a little later, but I want to start introducing that. So the w is kind of going to replace that inner function, so to speak, or be let to be equal to that inner function. So how does the chain rule work? Well, first thing to recall is that f prime of x, you have this notation, can also be represented as df dx as a fraction. And the great thing about this fractional notation is that it works like a regular fraction and can be split up. So you got this df dx, this would be equal to df over 1 times 1 over dx. There's nothing wrong with doing that. And furthermore, we can actually introduce an intermediate variable to facilitate this chain concept, where you have this outer thing and this inner thing, and you're putting them together, so to speak, in a chain. And I use w up above as my intermediate variable to kind of represent that inside function. So I'm going to do that here, and we will have then this df dx is actually equal to df dw times dw dx. And the dw's would cancel. You get back to the df dx. Again, very similar to how you work with regular fractions. But now what I have here is two separate derivatives. I've got the derivative of the outer function, the f from up above, times the derivative of the inner function. And that's going to be a huge part of the chain rule. That's really the chain rule. So let's use that result with this example here. And I'm going to let f of x equal this x squared plus 3 quantity raised to the 4th power. And I want to find f prime of x. In order to make this happen, I need to get the w into play. And the w, again, I've been letting equal the inner function, which would be the x squared plus 3. So that's just the inner function there. And then the f of w would be equal to the outer stuff, which is just essentially w raised to the 4th power. That x squared plus 3 is w, and that's raised to the 4th power. So this would be the outer function. And now, using this chain rule derivative approach, I can say that f prime of x is really equal to this df dx, which we split up to facilitate the chain, df dw times dw dx. And now, looking at this, df dw, so if I just look at the f of w function and find its derivative, what I get is 4w cubed using power rule. And then the dw dx, that's going to be the derivative of this w function with respect to x, and that's just going to be 2x. And I'd like to stop here, but when I look at the result, it's like I'm supposed to be finding f prime of x, and I've got a w in there. So how do we fix that? Well, we just replace it with what it's equal to. And it's equal to x squared plus 3. So we have this 4 times x squared plus 3 quantity cubed, and then times 2x. And if you simplify a little further, you'll get 8x times this x squared plus 3 quantity cubed. And that then completes the derivative using the chain rule process. And notice that what's really happening here is we kind of take the derivative of the outer, leaving the inside alone. If we look at this result right here before I simplified, you really just kind of took the derivative of the outer stuff, leaving that inside x squared plus 3 alone, and then you multiplied it by the derivative of the inside. And that is another way to think of the chain rule. You take the derivative of the outer function while leaving the inside function alone, and then multiply that result by the derivative of the inner function. And in notation, what this becomes is this d dx of f of g of x. So I'm going to use that composite notation because that's what the chain rule was designed for. And we will have the derivative of the outer, so f prime, leaving the inner one alone, so just gx stays there, and then multiplied by the derivative of the inner. And if there was another inner function, the chain would just keep going. You just keep working your way inside. You start on the outside, work your way in again, work your way in again, until you run out of things that are inner functions. So this, chain concept kind of makes sense if you think of it that way. Okay, and this is really the big thing you want to take away from this first page. So let's go ahead and look at derivatives of exponential functions. And in order to make this happen, there's a little bit of pre-stuff we got to do. So let's find the derivative of e to the x. We're going to see this is a very special derivative that plays a role in general bases. So we'll have the limit as h goes to 0, e to the x plus h power minus e to the x all over h. And then we got to use some exponent rules here, and we'll have e to the x times e to the h, splitting up that e to the x plus h, and then minus e to the x all over h. And then I can do some factoring since I have an e to the x in both of those terms. So we got e to the x out front, and then e to the h minus 1 over h, just grouping that together. And now e to the x doesn't have an h in it, so it's technically a constant relative to the limit. I can pull that out front, so e to the x. And now I got this limit as h goes to 0 of e to the h minus 1 all over h. It's like, okay, how do we evaluate that? And there's a lot of different ways that you can approach this and do this algebraically. If you Google it or whatever, you'll be able to find some other ways to do this. But I'm just going to look at a graph, because the graph here will tell the story. It'll give me the right answer. And, it's okay to use graphs to find limits. It's just something you can do. And when I look at it, I have this e to the x minus 1 over x, so I had to use the x instead of h in the software. But as I look, when the x, which is replacing the h, remember, goes to 0, so x goes to 0, notice that the derivative is 1 there. Or not so much derivative, sorry, the y value is 1, getting ahead of myself. So you got this e to the x minus 1 over x just going to 1. That limit is going to 1. So coming down here, we can complete the derivative of e to the x, and I'll have e to the x times 1, the limit value, and it just goes back to e to the x. So amazingly enough, the derivative of e to the x is just e to the x. And again, if you were to take other approaches at looking at that limit, it still results in a 1. It just goes to 1 no matter how you look at it, graphing, algebraically, whatever. And the derivative of e to the x is just itself. This is why base e is the favored base for calculus applications. It makes things so much nicer because the derivative of e to the x is just e to the x. It's crazy. So what about the other bases though? Because sometimes you run in the other bases when you're doing math, it'll happen, and you got to do derivatives of them. You're not working with somebody who likes base e for some silly reason. They might throw another base in there, and you gotta work with it. So let's take a look at this. So I'm going to let f of x equal a to the x power. So a is just some general base. You know, it could be 2, could be pi, could be 3, whatever. It's just a base. Could be e technically, but we're just going to say in general it's this a to the x. A is the base. Now I can write that using the exponential logarithmic relations. You know, there's properties of exponential and logarithmic functions that allow me to rewrite this exponential form as e raised to the natural log of a. So all of that is replacing a. E to the natural log of a is actually reduces down to a. That's a property of exponentials. And then I've got this x power still out there. Well, when you got a something raised to another power on the outside, you just multiply the powers together. So you got this e to the natural log of a times x, and this is all a power. And this is what I'm going to work with for the derivative. So I'm going to take the derivative of that. So dx of e to the natural log of a times x power would be equal to, and this is where the chain rule comes in, because notice I've got e raised to some power that is more than just x. So this inner function here is really like natural log of a times x. So to do the derivative using the chain rule, it's the derivative of the outer, which is the e raised to that power, and the inner just is left alone at first. So you do the derivative of the outer, and remember, e, the derivative of e is itself. So we just basically recopy that. And then we have to multiply that by the derivative of the inner function, which is the natural log of a times x. And coming down to the next line here, the e natural log of a x with all that in the power there, and then derivative natural log of a times x. Natural log of a is a constant relative to the x variable. So derivative of x is just 1, and that natural log of a just kind of carries along. So you got this. And then moving down to the next line here, I'm going to use this e natural log of a to the x, but I'm going to go backwards now. So I'm coming back this way, and I'm just going to replace it with the original a to the x power. And that completes the derivative for your general a of, or a to the x, power. So to summarize, the dx of e to the x is just equal to itself, e to the x, and the derivative of a to the x is just equal to a to the x power times natural log of a. And those two things are very important and should be remembered. You'll probably use this one a lot, but this one is also good to know if the base has been chosen or ends up being different than e. All right, thank you for watching.